Okay, hi everyone. Last time we learned how to find the Fourier series for a periodic function. So the Fourier convergence theorem was telling us if your function and its derivative is piecewise continuous, furthermore, if your function is a periodic function, then you can find its Fourier series, and Fourier series is equal to the function at the continuous points if your function is continuous at a given point. If your function is not continuous at a given point, then Fourier series basically gives you the average of the right and left limit. That's what we learned. We did a couple of examples, and we learned how to find the coefficients by doing the integration. Furthermore, we did some sophisticated examples. What I mean by that is basically, writing the Fourier series means expressing your function in terms of sines and cosine. If your function is already written in terms of sines and cosines, if the periods are matching, and then you don't need to compute the coefficients by using the integral. If you can just express in a nice one, you can easily find the coefficients, and you will see that in that case, most of the time, you will have only finite limit and non-zero coefficients. Okay. Now today we will talk about even and odd extensions, and then we will try to compute the Fourier series again. So before we do this, let's remember the heat equation, and then you'll learn why we need this thing. So remember, we had U sub t equal to alpha uxx, and we had the following conditions, and u 0t is equal to u lt 0. These were the homogeneous boundary conditions, and so it says like for the ends of your rod the temperature is always 0. And furthermore, we had the following. Initially when the time is 0, for x between L. So if you know the position on the rod, then initially you know what the temperature is. Okay, so if you think like this is our rod, so initially, if you are given a position x, this is the by the function f, then we know the initial temperature. And this thing says that at the ends, the temperature is always 0. These are the boundary conditions. And actually, we were able to solve this thing, but only there was a loss. We had the last step, but we weren't able to compute it. That's the reason we derive this Fourier series. So by using the separation of variables, so we did the following assumption: x of x and t of t, and with this assumption, and we were able to get the following thing. So you know all these steps, so we were able to get the following. So the solution was given as a series. So we had this unxt here and times cn, so which were basically cn e to the minus n square pi square over L square alpha square t times sine n pi over Lx. So this was the solution. The only thing was we weren't able to compute the coefficients, and for this we were going to use the initial condition, and so we got the following. When you plug in 0 for time, so if you plug in 0 for time here, and then this becomes e to the 0, which is 1, automatically you get the following. And from 1 to infinity, we have cn sine n pi Lx this way. So if you look at this side, This side is a Fourier series with period 2L. And on the other side, we have f of x. So how can we write this thing? Now, this was the question. But now, remember the Fourier series. If you are going to get a Fourier series, first of all, your function must be a periodic function. And furthermore, like if it's piecewise continuous, its derivative is piecewise continuous, then Fourier convergence theorem says that, yes, you can find its Fourier series. But there is one issue here, is the following. I mean, it says this function is equal to this expansion. So this is a Fourier series with coefficient Cn. Furthermore, it's a sine series, which means all the cosine part is 0. And we understand our function must be like it's an even function, so that we don't see any cosine terms. But we have the following thing. I mean, our function is not periodic. How can we get such an equality? How can I write a non-periodic function between 0 and L as a Fourier series? So we got stuck here. So then what we can do now? So I want to express it, but my function is not periodic. So what we can do is, if your function is not periodic, but if it is piecewise continuous, then there is only one issue, like you should take care. You have to make it periodic. So then, if I can make this function periodic with period 2L, be careful now, this is defined between 0 and L, then I can compute its Fourier series. So, but what should I do? First of all, I mean, this is given between 0 and L. So I have to extend my function between minus L and L. There's no problem between 0 and L. It's already here, given by this f. So we have to make a now extension. But that's not enough, because yes, now you extend it, your function is now defined between minus L to L, but then you have to make it periodic so you can compute its Fourier series. So that's the reason. First of all, we will make extensions, and then we will then make them periodic, so we will be able to compute the coefficients. So what I mean by this, so let's say that given f of x, which is f of x and its derivative are piecewise continuous. Okay, piecewise continuous on, okay, this. So I want to find its Fourier series. Be careful, I all just care about what is happening between 0 and L. So even if I extend it from if I extend it to the part from 0 to minus L, I mean, I'm not going to use it at all. I will just use the part between 0 and L. So just to apply the Fourier convergence theorem and to compute the Fourier coefficients, I'm just making the necessary steps. I'm taking the necessary steps here so that we can compute its Fourier series. So now, given a function, so now it's piecewise continuous, we will extend it to minus L to L, and then we'll make it 2L periodic. 2L periodic. In other words, f tilde x plus 2L is equal to f tilde f of x, where f tilde is the extension. So you will extend it, you will get f tilde, and then you will make it periodic. So what I mean, graphically, so we are just given a function between 0 and L. So let's say that we are given such a function, okay? We are given such a function. Only this is given. So now I can't compute its Fourier series. Yes, it's piecewise continuous. Its derivative is going to be piecewise continuous, but unfortunately, it's not periodic. And you make it periodic just right away, its period won't be L, so it won't be 2L, it will be L. So I have to make it 2L periodic. So if you look at here, and pi over L, to use such a thing, this function must be 2L periodic. Okay, then what will I do? Now I will extend it to the minus L part. So what is the extension? Now at this point, if nobody said anything, so it's up to you. You can just extend however you want. So for this example, I'm just going to extend it as 0. I'm just going to extend it as 0 because I'm just giving you an example. This is an easy extension. You could just do all other possible extensions. As long as you make it piecewise continuous, there is no problem. So don't send to infinity, minus infinity, or infinity. So this is an extension. Now, if you look at, now, this is now my f tilde. This is my f tilde. It's the extended function now. So after this, I will make it periodic. So now it's already 2L length. So L, 3L. Now you see, this is another period. So I will just copy and paste it here. So I will have this. Like this, and you can continue. And similarly, on this side, you can now continue. So this is minus 2L minus 3L, copy and paste. And like this. Now, this is the function we got now. So now for this function, we can compute its Fourier series. So because our function is now piecewise continuous, its derivative is piecewise continuous, and if you look at, it is now 2L periodic. So we can compute its Fourier series. But now when you compute the Fourier series for this function, you have to compute the ANs and you have to compute the BNs. Why? Because if you look at, according to my extension, this function is not an even function. So it's neither even nor odd. So because of this, we will have AN terms and we will have BN terms. So we need to compute those things because my extension doesn't have any symmetry right now. Even like I made it 0 just to compute it easily, maybe, because I just need to compute the integral from 0 to L. But I have to compute both ANs and BNs. I cannot escape from those computations. Okay, so you can make it anything you like if nothing is given. But according to your extension, you need to compute the ANs and BNs. But now, let's come back to the title. So if I make an even extension, or if I make an odd extension, what will happen? As we saw in our previous examples, if my extended function, my function between minus L and L is an even function, then we won't have any sine terms because sine is odd. So we won't compute any BNs. We will just compute ans for an even function or for an even extended function. Similarly, if our extension is an odd extension, and if you make it periodic, then in that case, you won't have any cosine terms. So you will just compute the bn's. Okay, that's what we need to do. So it may be told like, I mean, oh, do an even extension, do an odd extension, and compute the Fourier series. But depending on the problem, basically, I mean, you have to do an even extension, or you have to do another extension. For example, for this problem, for the homogeneous boundary conditions for the heat equation, eventually I will have a sine series. A sine series means there is no ans, no cosine terms. So this thing says that if you want to solve the heat equation with homogeneous boundary conditions for this function, you have to do an odd extension because you must get just the sine terms. So this problem tells you what to do. You have to do another extension because you need to get a sine series. So in that case, you will make an odd extension. So now let's do both the odd and even extensions for this given function. So okay, and okay, so I'm just repeating the same example just to give you a taste. So if you look at this was the function given. Now for the first one, I will do an even extension, and we know that even functions are symmetric with respect to the y-axis. So my extension must be, I have to take the symmetry of this with respect to the y-axis. So the graph will be like this. Now it's an even function. So this is now your f tilde. Let me just do the old way with the purple. So now this is your f tilde now. F tilde between minus L and L. And so now I will just copy and paste it. So what you're going to have is the following. So it will continue like this. Copy and paste here. Okay, so this is the even periodic extension. So function here, even extension, even periodic extension. So you make it even and then periodic. Now if you look at this, now odd functions are symmetric with respect to the origin. So I will take symmetry with respect to the origin. So then we will get something like this. Then after this, now I will copy and paste. So we will have like this. And Okay, so it continues like this. So this is odd periodic extension. So now the first one, the even one, will have cosine series, and this one will have sine series. So which means like here all bn's are 0, here all an's are 0. So you don't need to compute it. So that means like if you do such kind of extensions, even or other extension, at least your calculation is halved. So you just do less calculations. Either you compute the an's depending on the extension or bn's. As I said, depending on the problem, you have to do either an odd extension or an even extension. Okay, so this is what we had. Now let's do an example. So we are given the following function, f of x, which is 0 between and pi over 2. It is pi minus x between pi over 2 and pi. So the question is, find its sine series. And compute the sine series of this function at 5 pi over 2 and at minus 29 pi over 2. Okay, this is what we have. Now let's first of all draw the graph of this thing, just to see now what's happening. So now I'm going to have its sine series. Okay, so that tells me you are given the function between now 0 and pi. So first of all, you have to make it an odd function to get a sine series, and also then a periodic function. So what should the period now? This is the half of the period because I'm given between 0 and pi. If I extend it an odd way, I will get the 1 period. So my period must be just from minus pi to pi. So it must be 2 pi. So then I need to extend it to, first of all, minus pi to pi in an odd way because I'm looking for a sine series. So what was the actual graph of this one? So if you look at the graph of this one, between 0 and pi over 2, it is 0. But between pi over 2 and pi, it is pi minus x. So it's a line equation. If you plug in pi, you get 0, but it's empty. Now, if you plug in pi over 2, you get pi over 2. So it is something like this. Okay, so this is the graph of the function. Now, I will extend it in an odd way. So then, with respect to the origin, its symmetry is this one again. Now, symmetry with respect to origin will be this. Okay, so symmetry now. And now, let's make it, we made it now odd extension. So now I will make it periodic. So after this, we will just copy and paste. So this piece will come here. And this piece will come here. So we will have this part. And so on. Similarly, now this piece will come here. So and that purple piece will come here. Here. Now, this function is odd. It is, and it is a periodic function with period 2. So if you look at now, we have f tilde. F tilde means this purple and pink ones together. And now if I add 2 pi to any number, any x, so it will give me this. Now you can think, okay, you are doing an extension, so this will affect your computation because you need to integrate from minus pi to pi. Now let's see. So it is an odd extension. It's an odd extension. So odd extension. So this will imply all ANs are 0. So I don't need to compute any ANs. Because even in the question it says you look for a sine series. So how about BNs now? Okay, now BN, remember the integral is from minus L to L. Here L is pi, so from minus pi to pi. 1 over L, which is 1 over pi. Our function f tilde, because between minus pi to pi, I need to integrate f tilde. That's the extended function. And so times sine n pi over L. L is pi x dx. This is what I need to compute. So now I can cancel the pi's here. Now I need to integrate this. But now look at the following. So f tilde was an odd extension. So it's an odd function. And similarly, sine is an odd function. So if you look at the product of two odd functions, you get an even function. So as a result, I don't need to integrate from minus pi to pi. I can just integrate from 0 to pi, and then I will double my integral, 2 over pi. But between 0 and pi, it is already my function, because between 0 and pi, I'm going to use the function itself, not its extension. So I will use f of x times sine n x dx. So as you see, like, I mean, even we extended it in the computation, we are not using the extended part. And we are basically extending that way in an odd way to just apply the Fourier convergence theorem. Otherwise, because we won't be able to get a Fourier series. So that's the reason even we had the odd extension. While computing, again, we will use the old function, the not extended function, f of x, between 0 and pi. But be careful, we are doubling here. So then what do we have here? We have 2 over pi from 0 to pi. But be careful, I mean, I'm integrating from 0 to pi. Now, let's focus on the function. Between 0 to pi, I need to integrate. But between 0 and pi over 2, my function is already 0. So I don't need to integrate that part because f of 0 times sine is 0. So that means it reduces just the integral from pi over 2 to pi, because my function is non-zero just there. So from pi over 2 to pi, there my function is pi minus x. And so sine nx dx. This is what we have here. So I need to do this integral. And so what we are going to do, so this is a product. So I will say this is my u, this is my dv. So I will use integration by parts. So if you do integration by parts, so let's write here, u is equal to pi minus x, dv is equal to sine nx dx. So du is equal to minus dx, v is equal to minus cosine nx over n. This is what we have. And so from here, we get the following, u times v, which is minus pi minus x cosine nx over n from pi over 2 to pi, minus from pi over 2 to pi integral of v times du. So now v is cosine nx over n with a minus, so it makes it plus. But du is minus dx, so it makes it minus again. So we get this. Okay, so if you multiply these two, you get plus. So we go back to the old version. So now after this, let me just write here. Pi minus x is x minus pi if you just do this. X minus pi times cosine nx over n. If you look at the integral of this, antiderivative is sine nx divided by n. So there's another n here. So we have minus sine nx over n squared all together from pi over 2 to pi. This is what we need to do. Okay? Now, let's compute those. So if you plug in pi, now let me just show here. If you plug in pi here, pi minus pi is 0. So this goes away. If you plug in pi, sine n pi, we get sine n pi is also 0. Which means when you plug in pi, you get 0. So we get 0 minus now. When you plug in pi over 2, when you plug in pi over 2 here, pi over 2 minus pi, which is minus pi over 2. So cosine n pi over 2 over n. So we have minus pi over 2 cosine n times pi over 2 over n minus sine n times pi over 2 over n squared. This is what we get. All right. So if you look at this is minus makes it plus. So this is becoming plus. So if you want, you can do this here anyhow. But let's see what's happening. So cosine n pi over 2. Cosine pi over 2 is 0. But if n is even, then you get a multiple of pi. There, cosine won't be 0. So cosine will be either minus 1 or plus 1. Now, when you come to this part, when n is an odd number, then you get a multiple of pi over 2, odd multiple, and this will give you either minus 1 or plus 1. But if n is an even number, in that case, this will give you a multiple of pi, which will be 0. So when n is an even number, this part will be 0. When n is an odd number, this part will be 0. So depending on evenness and oddness, one of them is going away. So then what do we get then? Let's write it. If you write when n is equal to 2k even, n is equal to 2k minus 1. So k is starting from 1. When n is 2k, in the even case, this part will be 0. So then what are you going to get? What are you going to get? So we have minus, we get plus. We have pi over 2n. And now n is 2k times cosine 2k. Now 2's are canceling. We get cosine pi k. But cosine pi k, when k is odd, you get minus 1. When k is even, you get plus 1. So we get then actually just minus 1 to the k here. All right. Now, if you come to the odd case, in that case, minus makes it plus. So we just have 1 over n squared. 1 over n squared. So, what about n is 2k minus 1? So, and then now, if you come to this, 2k minus 1, k is starting from 1. So when k is 1, for example, you see it is plus 1. When k is 2, you get 3. So sine 3 pi over 2 is minus 1. So when k is odd, you get plus 1. When k is even, you get minus 1. So then this should be like this. So for even ones, you are getting minus. For odd ones, you get this. So these are the coefficients. If you want, you can write a few terms of it. For example, if you write f of x, basically f tilde x, you could say. But if you are taking between 0 and pi, you can just write that way. So here, x is between 0 and pi. So if you write a few terms, for example, what is the coefficient of sine? So n is now 1. So we have sine x. What is the coefficient of sine 2x? What is the coefficient of sine 3x? So it goes like this. Sine x now, its coefficient is 1. 1 means it's an odd number. If it's odd, now you are here. When n is 1, k must be 1. If k is 1, then we have here plus 1. If k is 1, you have 1 over 1 square, which is 1. And then now, sine 2x, 2 is even. So we will have pi over 2 times 2. So we have pi over 4. Now k is 1. If k is 1, this will be minus 1. So we will have minus pi over 4. Similarly for 3x, now 3 is this one. K must be now 2. If it is 2, this will be negative. And so we will have 1 over 2 squared, which is 1 over 4. So we have minus 1 over 4. So it goes like this. This is the Fourier series. Just a few terms between 0 and pi. This is what we have. Now let's go back to the question. So we were also asked to compute. We were asked to compute the certain values. So what were those? Let me check. So SF, now 5 pi over 2. Now if you look at 5 pi over 2, actually I erased the board, but so we know what's happening between minus pi over 2, minus pi and pi. But this is not there. So this is bigger than pi, so it's 2.5 pi. So now what we can do, we can just take it back. We can just, because it's a periodic function, so if you just subtract multiples of period, nothing changes. So this thing says that if I subtract 2 pi, it won't change. Because my period is 2 pi. I can subtract 2 pi. If you do this, then we get SF pi over 2. Now what's happening at pi over 2? Remember the graph. One side was 0, the other side was pi minus x. So we had a jump discontinuity. So for this now, we have to check the f pi over 2 plus right limit pi over 2 minus left limit and take their average. So if you remember right limit, we're just going this way. So if you look at the right limit, sorry, here, it goes to pi over 2. Left limit goes to 0. So we have pi over 2 plus 0 divided by 2. We get pi over 4. So for the other one, minus 29 pi over 2, that's, I guess, minus, yes. Now what you can do again, now this is on the left side, you can just add multiples of 2 pi, so you can put in the interval. So this is like 14.5. So if I add 14 pi, how do I add it? I add 7 times 2 pi. Because my period is 2 pi, its multiples won't, when you add its multiples, it won't change. So if you do this thing, then this is going to be now minus pi over 2. Now this time, if you look at the right limit and left limit, let me just write them directly. Right limit will give you 0, but left limit will give you minus pi over 2, because the graph was below, and divided by 2, you get minus pi over 4. This is what we have. Okay. Maybe as an exercise, you can do the following. How about exercise? How about is F10. What is this? You can find approximately the location of 10. So that will tell you what the answer is. All right, so now this was the odd and even extensions. So you depending on the problem or depending on your choice, you can make an odd extension or an even extension. So in those cases, you will have either sine series or cosine series. Basically, this way you can have less computation. Either you compute ANs or BNs. All right. Now, let's solve an heat equation problem. So, after driving all those things, actually, what we learned is if you are given a homogeneous heat equation, which means like if the ends are both zero temperature, then it's all about computing the Fourier series of the initial condition. So that's why I will just do this problem very quickly, because I want to do an extra problem where we need to do those computations again. So we are given the following problem. So u sub t is equal to u sub xx, and we have u0t and u40t is equal to 0. And these are your boundary conditions. Now your initial temperature is given as 50. So now if you look at, according to this now, your x changes between 0 and 40. So x is between 0 and 40. Now, what is the solution to this problem? Again, I mean, you need to do separation of variables. You'll do all these things. But actually, we did all those computations. So if you do this thing, if you look at here, so here, alpha square, which is the thermal diffusivity constant, so that was the coefficient here, now it's 1. And actually, we could directly write the solution. I mean, because it's the same problem. I mean, we solved at the beginning and nothing changed. Just now here, L is 40. So L is 40. And 50, which is the constant function. So this is your f of x. So by knowing this, I know the following. uxt, the solution was, and from 1 to infinity, now we had Cn, or you can now call them Bn if you want, because we will have just the sign. So e to the minus n squared pi squared over L squared. L is 40. 40 squared times alpha squared, which is 1 t, and times sine n pi over 40x, where the Cn will come from the following thing. So when you plug in 0 here, 50, which is your ux0, and this must be equal to n from 1 to the infinity. We just have Cn. If you plug in 0 here, this is 1 sine n pi over 40x. So it says that now you should write the Fourier coefficients here, but it must be a sine series for which function? The constant function 50 between 0 and 40 for x. So then we can just directly compute it actually. I mean, if you want to do what theoretically, I mean, you can actually directly compute, because after this example we know what to do. But anyhow, let's show the steps again. So I have to do another extension for this constant function 50, and first of all I need to extend it. So if you look at now, so this is 40 and this is 50. Now this is minus 40. So we have now the constant function 50 here. And now I need to find its sine series, so I will extend it odd way. Okay, so this is what we have. Now actually this is minus 50. So then after this, you will make it periodic with period 80. So it goes like this. Now, for this, we need to compute the bn's, because the n's are all 0. So now what is going to be bn? Bn is going to be 2 over L, which is now 40. I just need to integrate from 0 to 40. So I'm just skipping the first part. So I need to integrate from minus 40 to 40. So my extended function is odd, sine is odd, the product is even. So I need to integrate from 0 to 40, but I have to double my integral. So this is basically the thing. Between 0 and 40, my function is 50, constant. So I multiply with sine n pi over 40x dx. So if you do this integral, so we have just 100 over 40. So which is 10 over 4 here. And entire derivative of sine is, now here we have minus cosine n pi over 40x divided by n pi over 40 from 0 to 40. Okay, this is what we have. So if you plug in now, maybe let me just do it here. So if you plug in 40, so this x is 40, 40, 40 cancels. We have just this 10 over 4 parentheses. We have minus cosine and pi, and over n pi over 40 minus, now another minus is coming from here, which makes it plus. Now if you plug in 0 here, we have cosine 0, which is 1 over 40. This is what we have. Okay. Now what do we get here? If you look at when n is even or odd, this will be either minus 1 or plus 1. When n is odd, cosine n pi will give you negative 1. Negative, negative makes it plus. So we have 1, 1, 2. So we have 2 over n pi over 40. When n is even, cosine n pi will give you 1. So we have -1, -1, +1, we will get 0. So only for odd terms we will have non-zero coefficient. So if you do this, let me just make it a long equality here. So we have here 40 over n pi. So we have 40 times 10 over 4 times n pi. And now when you, this is going to be just 2. But here only this is when n is odd. Okay, otherwise it's going to be 0. So you can just do the cancellations and you can get the coefficients. But I want to say one thing here. So how about, I mean, the ending behavior of this function? What will happen as time gets larger and larger? So what happens as time goes to infinity? So what will happen? So think about the realistic problem. I mean, you have a rod and you are freezing the ends basically. You are putting them in an icebox with temperature 0. So eventually, whatever the initial temperature is inside, so eventually, I mean, basically you are freezing it from the end. So the initial temperature may be high, but it will get lower and lower and lower and lower. Eventually, I mean, the temperature must go to 0. So basically, this is also what you can see here. So if you look at to understand what is a steady state solution, like what will happen eventually if you take the limit as t goes to infinity for this. Now, in this problem, if you look at, just think about, I'm taking t larger and larger. If t gets larger and larger, e to the minus, so your exponent is getting larger, but because of minus it's getting, so it's getting negatively larger. For an exponential with bigger and bigger negative exponents, this part will go to 0. And so whatever this part is, actually it will push this thing to 0, because if you think about, like, I mean, you can use squeeze kind of theorem, so squeeze theorem. So I mean, if you take the absolute value of this, it will be I mean, trapped by the one side, which will be negative of this, one side positive of this. So that's the reason this will make this thing going to 0. Because, I mean, here, whatever the bounds are, maybe let me just do it this way. So if you look at the absolute value of Cn times e to the minus pi n square pi square 40 square t times sine n pi over 40x. This is always bigger or equal to 0. And this side, this has the biggest values, most 1. So we have just Cn. And forget about Cn actually. I'm just computing the coefficient, just what's happening for the functions. So if you look at this is just less than this one, e to the minus n square pi square 40 square t. So this part is going to 0. This part is going to 0 by squeeze theorem. The mid part must go to 0. So every term here is going to 0 as t goes to infinity. So that means your series, your function, will go to 0 eventually. So we got 0 here. All right. So we did one example of a heat equation. So now let me just do one final example and finish this semester's last lecture. Let's do another heat equation, but this time let me change my conditions. So we are given 2 times uxx is equal to u sub t. So this is the classical heat equation. So now we are given x is between 0 and 6 and positive. But now if you look at our conditions, in this case, I didn't give you any initial condition now. And so maybe let me just write the initial condition and altogether we can solve. And the initial condition is okay, so this is what we have. X is between 0 and 6. Now, so if you look at now this problem, we are trying to solve the heat equation. So we have one-dimensional object, so on a rod. So now again, we have a rod. But this has now length 6. So now here we have x. This is the position 0. This is the position 6. So it says that initially the temperature distribution is given by this function between 0 and 6. But now this is if you look at the boundary conditions, these are different boundary conditions because the one we solved was the temperature at the ends were 0. So you are fixing the values at the ends. But now this time we are not giving you the fixed values, we are giving you the change at the end. So it says the derivatives at the ends are given 0. So basically the change at the ends is 0. The temperature at the end is not changing. So at these ends, temperature is not changing with respect to x. That's what we're given. So basically, I mean, the previous problem is called Dirichlet problem. So when you fix the values on the boundary, when you fix the values on the boundary, it's called a Dirichlet problem. When you just give the change on the boundary, now if you look at this is like the change this direction. So if you are given this, then this time it's called Neumann conditions. So basically now we are trying to solve this Neumann problem for the heat equation. Now how are we going to solve it? So again, alpha squared is 2, but the problem is totally different now. I mean, so I have to do all those steps again. I mean, I cannot jump to the conclusion like I did for the previous problem. So what will I do? I will now suppose again by using the separation of variables. So I will assume uxt is equal to x of x, t of t. Okay, so this is what we have. And this time, our equation is still same. So this gives us the following. I mean, it's the same heat equation. So we have 2 times x double prime times t is equal to, we have x times t prime. Again, if you do the separation, so if you do the separation, we get x double prime over x is equal to t prime over t. And if they are equal to each other, we know that they must be constant. So we said it's minus lambda. This is what we have now. Okay, so from this we get the following. equation. It's basically ordinary differential equations. So the first one, let me just write this, t prime plus lambda t is equal to 0. Second one is x double prime plus lambda x is equal to 0. Now, if you look at the conditions, our conditions were u sub x 0t. This is 0. So if you write this, this is going to be x prime times t of t, because I'm just taking the derivative with respect to x, and now x is 0. So this is going to be 0. Again, if t of t is 0, then I will get the trivial solution, the 0 solution. Okay? If t of t is equal to 0, so we get complete the trivial solution. Okay? So this implies then, so t of t 0, which gives us u of xt is 0, which is the trivial solution, or x prime of x is x prime of 6. So I'm sorry, x prime of 0 is 0. This is what we get. Okay, this is the thing. And similarly, if you write the other condition, u sub x 6t, this time it will be x prime 6 t of t. From this one, again, either I will get the trivial solution, or basically I will get x prime 6 is equal to 0. Okay. This is what we get. All right. Now, that means I can start from anywhere, but of course, I mean, since we got these conditions for x, now I can use these conditions to find the possible x's also for lambdas. For possible lambdas, I will try to find x. Again, we will need some like eigenvalues and eigenfunctions to solve this problem. Okay, let's now go ahead. So what we were doing, like we were trying to solve this thing. So now I will come back to 1. So if you look at here, the characteristic polynomial is r squared plus lambda, characteristic equation, you can say. So what we have now, case 1, the case 1, now lambda is negative. If lambda is negative, we get r squared, a negative number, so you can take to the other side. So you can take square root, you will have 2 roots. So this time, then our solution will be x of x is equal to c1 e to the square root of minus lambda x plus c2 e to the minus square root of minus lambda x. This will be the solution. Now, I need to plug in these conditions. So if you plug in these conditions, let me just do it here. I need to plug in them to the derivative. Now, if you plug in them to the derivative, so the derivative of this x is now equal to C1 square root of minus lambda e to the minus lambda x plus C2 the minus square root of minus lambda x. So it says if you plug in 0, you get 0. Now, if you plug in 0 here, e to the 0 is 1, e to the 0 is 1, so we get C1 minus C2 with this parenthesis. So we have minus lambda, we will have C1 minus C2. Okay, so this is what we have. Now, the second one tells x prime 6 must be 0. So if you plug in 6 here, so we have now C1. Okay. Again, we will have this parentheses square root of minus lambda. Now at this time we will have C1 e to the square root of minus lambda times 6 and minus C2, yes, minus C2 e to the minus 6. This is what we have. Now, if you compute C1 and C2 here, for example, this thing says that C1 has to be equal to C2. So if you write here in the place of C2, if you write here C1, since these numbers are not equal to each other, if you want to get 0, then both C1 and C2 must be 0. So that's the only way you will get this thing. So C1 and C2 are both 0, which says that in the case 1, we have the trivial solution, which is the 0, and so again we don't get something new. Now let's look at case 2. Case 2 now. Case 2 says now lambda is 0. This time you have double root, and so the solution will be C1 e to the 0x, so it's 1, plus C2 times x times e to the 0x, which is just 1. So this is the thing we get. Now I need to, what about its derivative? Its derivative is just going to be C2. Okay, so what does this thing say? So we have x prime 0 must be 0, and x prime 6 must be 0. But what is x prime 0? X prime 0 is C2. X prime 6 is C2. So it says C2 is 0. So then what do we get? So this gives us x of x is basically C1 times 1. So it says 1 is a solution to this. Any multiple of 1 is a solution too. So this is what we get. So we found at least a non-trivial thing here, 1. Okay. Now let's come to the last case. So I need to erase now. Last case. All right, so case 3. Now lambda is positive. This time you will have complex roots, square root of lambda I minus square root of lambda I. So this time our solution will be C1 cosine square root of lambda x plus C2 sine square root of lambda x. Now, if you take the derivative, because I need to plug into the derivative, so this comes here with a minus c1 square root of lambda sine lambda x and plus c2 square root of lambda cosine square root of lambda x. This is what we have. So the conditions are x prime at 0 must be 0. So if you plug in now 0 here, sine 0 is 0, cosine 0 is 1, so we get c2 times radical lambda. So this is what we have here. Right. And then now x prime 6 is equal to 0. And that time we will now actually from this thing we can directly say the following. I mean, if c2 times radical lambda is 0, then c2 has to be 0 because we know that lambda is positive. So this is not 0. So that this means c2 is 0. So c2 must be 0. So here this part is 0. So I can just consider like this part is 0. So I can just focus on this part. So if you look at, we have minus c1 square root of lambda times sine square root of lambda times 6. Okay. So again, when can we have a 0 here for this value? Either this is not 0, it's positive. So either c1 is 0, but if c1 is 0, since c2 were 0, altogether we get x0, we get the trivial solution. But now, then, there's only one possible thing here. Either this is 0, which gives us, again, trivial, or this part must be a multiple of pi. Because if this part is a multiple of pi, then sine will be 0, so we get this. So this implies, if you are looking for non-trivial thing, so square root of square root of lambda times 6 must be equal to n pi. So otherwise, c1 is 0, which gives us nothing other than the trivial solution. So this thing says that then square root of lambda is equal to n pi over 6. So then what did we get now? Here, where so this is n is now n is 1, 2, 3, like this. Okay. So then what will we get? So either for these we have this lambdas, for which now we have just this part as the solution. Because if this is 0, then c1 can't be anything. And also for lambda equal to 0, we have this as the solution. So if you look at now, if you look at this, then we can group them in the following way. So I can include like n is equal to 0. If n is equal to 0, basically radical lambda is 0. In that case, my solution is just c1 times 1. So then we can write everything in the following way. So for n now equal to 0, we have so 1, 2. For each of them, basically we get the following solution. If you look at here, I'm just going to write cosine. So here, now radical lambda is now n pi over 6 x. So its coefficient can be anything. So cosine n pi over 6x. So this is a solution. Any multiple of this is a solution. So you could, again, call this thing eigenfunction. Be careful now, when n is 0, this part becomes 0, you get 1, which was basically the solution we got for the lambda equal to 0 case. So basically, these are all your eigenfunctions starting from 0. Okay. So how about now for these? How about the tn's? Now, if you look at the 1, we had t prime lambda t equal to 0. This was again the same equation as we saw in the heat with homogeneous conditions. So the solution will be from this t of t will be equal to just e to the minus lambda t, and any multiple of this is going to be. Now, be careful. For each lambda, we are writing a corresponding t. So then, now, if you look at this one, for n from 0, 1, 2 goes like this, then lambda is equal to n square pi square over 6 square. Now this is what we have. In this case, xn, the solution for x is going to be cosine n pi over 6. And for this n, we need to solve t, and t will be e to the minus n square pi square over 6 square t. So again, I mean, any multiple of this is a solution. Any multiple of this is a solution because you are solving homogeneous. Now you can multiply them, xn and tn, so then you get n, which is xn x times tn t, which gives you, let me just do this way. So e to the minus n square pi square over 6 square t times cosine n pi over x. So now these are, each of them is a solution. So since, again, if we have a homogeneous equation, their summation is a solution. So we get the following solution. So then we have uxt, and from 0 to the infinity, we have cn times un. Not only these, their multiples are also solution. What I mean is, like, if I'm thinking the following way: u sub t 2 uxx equal to 0. So here, this is an homogeneous equation. That's the reason if you have solutions, their linear combination will be solution. So we have n from 0 to the infinity. We have cn e to the minus n square pi square over 6 square t, and cosine n pi 6x. Okay. But now, if you want, you can separate when n is equal to 0 case. When n is equal to 0, we have c0. And this is going to be now, when n is 0, you have e to the 0, which is 1. When n is 0, cosine 0 is 1. So basically we have c0 plus n from 1 to infinity, cn cosine and pi over 6x. Now, basically we solved the problem, but we didn't impose the now initial condition. So now we need to impose the initial condition. So when you plug in the time is equal to 0, we basically get the cosine series c0 and from 1 to infinity cosine cn cosine and pi x. This is what we have. And this is supposed to be now equal to the initial condition. What was the initial condition? Let me rewrite it. We have pi plus 3 times cosine pi x minus 4 times cosine 3 pi over 2x minus cosine 3 pi x. So if you look at this thing now, on this side you see basically a cosine series also, but only with finitely many terms. And here also we are trying to find a cosine series of this function. So if your function is already expressed as a cosine, in terms of cosine with finitely many terms, that means then basically by just matching the coefficients, you can write the cosine series. So, but now what do you see here? We see pi. Pi is our constant. On this side, there is only one constant, that is c0, which means c0 must be pi. So c0 is then pi. This is the first thing. Now, on this side, we have cosine pi x. So when do we have pi x? Here, to get pi x, so n over 6 must be 1. So when n is 6, then I get cosine pi x. So when n is 6, this is my c6. So that means c6 must be equal to then 3. So that must be 3. So when do we have 3 pi over 2x in the cosine? So to have it, now if you want this, now this number, n over 6 must be 3 pi over 2. Okay, so n over 6 must be equal to 3 over 2. So it's 1.5. So then if you take n equal to 9, then 9 over 6 is 3 over 2, then we get C9. So C9 is equal to minus 4, and for this one, I need to get 3 pi. For this thing to be 3 pi, n must be 18, so we get 3 there. So C18 is equal to minus 1, and all others are 0. Otherwise, Cn is 0. So now we didn't compute anything here. We're just using the idea that Fourier series is writing in terms of sines or cosines. Here we need to write in terms of cosines. Oh, it's already written. Our initial condition is already written in terms of cosine. We just do the matching for the coefficients so we can get the number. So this is the number. So then if you write it, now if you write the complete solution, we have only finitely many terms, so we can write the complete thing. So then uxt. Now, if you look at the solution, we need to write C0, which is pi, plus Now, let me just tell you. So I'm just using this solution. I'm just replacing the coefficients. So when I get C0, it's here already constant. C6 is 3. So we have 3. And there we will have e to the minus n is now 6 square pi square over 6 square t times cosine, and it's 6 now, 6 over 6 is 1, so we have cosine pi x. Now we have minus 4, now n is 9. We have e to the minus 9 square pi square over 6 square times t cosine 3 pi over 2x minus, now C18 is minus 1, and so we have e to the minus 18 square pi square over 6 square t times cosine 3 pi x. This is what we have. And if you look at the steady state solution, which means what happens as t goes to infinity, so for this problem, even it's not asked, but let's try to answer it. As t goes to infinity, now if you look at this one, obviously, I mean, just you're not thinking like x is fixed. You're just taking the limit as t goes to infinity. Again, now this part is fixed, but this part now, as t goes to infinity, it will go to 0. Similarly, this part will go to 0. This part will go to 0. So 0 times that things, again, like we did a squeeze theorem. So we basically get 0 for these things, but only this one is remaining. So the answer will be pi. That's what we have. Okay, so this is the final answer we will get. All right. So this was the last thing I wanted to do. So I wish you good luck in all your exams.